Hello everyone, and welcome back to The Explainer. Today, we're exploring something absolutely fundamental. I'm talking about a phenomenon that invisibly dictates our everyday reality, literally from the moment you wake up to the moment you go to sleep. We're looking at the hidden force running our lives, electromagnetism. I am super excited to break down the science behind this with you today, so let's get into it.
Okay, so let's kick things off with a question that might seem kind of strange at first. What connects a massive, sky-splitting lightning bolt to a tiny, quiet compass needle resting in the palm of your hand? I mean, on the surface, they look like completely different things, right? One is this raw, explosive release of energy, and the other is just a gentle, steady, directional pull. But as you'll see in just a minute, they are actually two sides of the exact same coin.
Section 1. Basic Principles of Electricity and Magnetism.
Let's start by looking at electricity. At its absolute core, electricity is just the phenomenon associated with either stationary or moving electric charges. What's absolutely crucial to understand here is that the root source of this charge is an imbalance. When you have an imbalance of elementary particles like electrons, which carry a negative charge, or protons, which carry a positive charge, bam, you get electricity. It's basically nature's way of dealing with that imbalance.
To make this a bit more concrete, think about some everyday examples. Lightning is a massive scale example. The electrical current flowing from your wall outlet or, your phone's battery is another. Even the static electricity that shocks you when you grab a doorknob in the winter, that's all part of the same family. And the golden rule governing all of this? Positive and negative charges attract each other, while like charges, say two negative electrons, will always repel.
Now let's flip over to our second character, magnetism. Magnetism is the physical phenomenon produced by moving electric charges. Much like electricity, magnetism is all about forces that create attraction and repulsion between objects. But, as we're going to discover, the origin of this attraction and repulsion has a very specific trigger.
And you interact with magnetism just as often as electricity. Think of that compass needle reacting to the Earth's massive magnetic field, or just the simple bar magnets you played with as a kid. But it actually goes way deeper. The field surrounding electromagnets, the hard disks inside your computer, even the internal navigation systems of migrating birds, all of these rely completely on magnetic fields to function.
Okay, I know. Throwing a giant table of units at you can look intimidating, but stick with me. Let's synthesize this. Notice how we isolate these behaviors. On the top half, we measure electricity in really familiar terms like amperes for current, volts for potential difference, and watts for power. But down on the bottom half, magnetism uses units like the Tesla for magnetic flux density or the Weber for magnetic flux. Having these totally distinct measurements helps scientists isolate their behaviors, even though, as we are right about to see, they are actually deeply intertwined.
But before we mash them together, we need to highlight a critical structural difference between the two. Over on the electricity side, it's based on positive and negative charges. And importantly, monopoles do exist. You can totally have a lone positive proton or a lone negative electron. But switch over to the magnetism side. Any magnetic object always has a north and a south pole. No known magnetic monopoles exist anywhere. If you take a magnet and chop it right in half, you don't get a separate north and south. You just get two smaller magnets, each with its own brand new north and south pole. Pretty wild, right?
Which brings us to Section 2, the electromagnetism plot twist.
So here's the deal. You can absolutely have an electric field without a magnetic field, like a stationary point charge. And you can have a magnetic field without an electrical current, like that permanent magnet stuck to your fridge. When things are just sitting perfectly still, they exist totally independently. But there is a massive catch when things start moving.
And here is that plot twist in action. Watch what happens here. The moment an electric charge actually begins to move, a magnetic field ripples out and is born. Now look at the flip side. If we take a moving magnetic field, it forces electric charges to move, which produces an electric current. So the absolute crucial takeaway here is that motion is the secret key. Motion is what links these two seemingly totally separate phenomena into a single unified electromagnetic force.
And watching this animation brilliantly illustrates what happens when they travel together. Notice how they're perfectly perpendicular, oriented right at a 90-degree angle to one another. They're locked together in this endless, undulating wave of energy. In an electromagnetic wave, which, by the way, is exactly what light is, the electric field and the magnetic field travel in the exact same direction, just dancing together forever.
Moving right along to Section 3, Maxwell's 4 core rules. Let's break down James Clerk Maxwell's first rule. It deals strictly with electric charges. As we already covered, like charges repel and unlike charges attract.
But the important math behind this is that the force of that attraction or repulsion is inversely proportional to the square of the distance between them. Basically, in plain English, as two charges move further apart, the invisible force between them drops off drastically. Distance dictates power.
Rule 2 just firmly cements what we discussed earlier about magnetic poles. They must always exist as north-south pairs. Again, magnetic monopoles simply do not exist in the known universe. And exactly like electricity, like poles repel like and opposite poles attract.
Okay, I want you to actually do this one with me at home so you can interactively visualize Rule 3. Hold up your right hand. Yeah, literally hold it up. Step 1. Point your right thumb in the direction of an electrical current moving through a wire. Step 2. Just curl your fingers inward. The direction your fingers are curling is the exact, clockwise or counterclockwise, direction of the magnetic field being generated around that wire. Scientists famously call this the right-hand rule.
Finally, Rule 4 covers electromagnetic induction. Watch this animation carefully. As that loop of wire moves toward the magnetic field, that pure physical movement magically induces an electrical current inside the wire. And if you move it the other way, the current literally reverses. The direction you move the wire dictates the direction the current flows. This exact principle is how we generate almost all the electricity in our modern power grid. It's a real game changer.
Section 4. The force running daily life.
Now, why does all this matter? Because except for the pull of gravity and nuclear forces, nearly every single occurrence in your daily life stems from the electromagnetic force. It dictates how atoms interact with each other to form chemistry. It controls the flow between matter and energy. Get this, when you touch a table and it feels solid, you aren't actually touching it. The electrons in your hand are electromagnetically repelling the electrons in the table. How crazy is that?
It is honestly fascinating to track how long it took humanity to figure this out. Looking at the timeline here, we start way back in the ancient era, where the Greeks noticed static electricity from rubbing amber, which they called electron, and magnetic attraction from lodestone, which they called magnetis lithos. They thought they were totally unrelated. It literally took until 1873 for Maxwell to mathematically unite them. But Maxwell's equations actually contradicted classical Newtonian physics. It wasn't until the 20th century that Albert Einstein used his theory of special relativity to finally resolve the conflict, proving once and for all that magnetic fields are just electric fields transformed by the relativistic effects of motion.
Which brings us to our final slide and a massive question to ponder as we wrap up. If a single, invisible, brilliantly intertwined force dictates everything from the very atoms making up your body right now to the hard disk in your computer storing your files, how does it shape the rest of our vast, expanding universe? Once you realize that motion is the bridge between electricity and magnetism, you really start to see the entire cosmos in a whole new electric light. Thank you so much for joining me on this explainer today. Keep asking questions, keep visualizing these concepts, and I will see you on the next one.